Well, just John Black, super chemist. I finally figured out the last thing about simultaneity. Okay, I'm just going to talk about this one thing. I have 6 or 7 videos in the series. You can go watch it if you want to hear the rest of it. Here we're just going to talk about, this 3 people are going half C this way, right? This guy's standing still. If the blue and the red guy at the same exact time hit a flashlight and try to hit this black guy, if they're standing still, the light beam should hit him simultaneously. Everyone should agree. Everything, they'll say light is the speed of C. Now what we did, right, when we changed it to moving and had this guy standing still, we said that C, right, the speed of the photons was going to be C relative to the standing still guy, relative to this type of photon clock. These people don't have this type of photon clock, right? So we put C up here. We said if this was driving by, what would this green guy see? Obviously, we're not woke, so we're not going to say he ain't going to see nothing. Okay, that thing is going to have to see that green guy ain't going to see nothing. But if we had a green photon detector right here, and right at this point where they were lined up in this configuration, the blue and the red guys did their flashlight, right? At that point, yes, if you had a photon collector, because we're talking about a billionth, 10 billionths, 100 billionths of a second here, okay? But if they did it at the same exact time, we said that it was C, right, relative to the green guy. So it's just going to come off at C. This is going to come off at C. There's an equal distance between them. So the first few photons before they, they're going to half C. They're not going to be there that long, right? But they will hit this green man at the same exact time, and this green man or detector will say that the blue man and the red man hit their trigger on their photon gun at the same exact time. So that is simultaneity, okay? But what the green man sees about the black guy getting hit, that's retarded, okay? Everything's going to be compressed on this side because this is going towards them. These things are going away, so it'll be more red shifted and more blue shifted over here. So far, the green guy fits perfectly into all of our things, you know what I mean? But then we have to go to the black frame, right, that's moving. We said that, so if it's C relative to this clock, right, then it has to be C minus this velocity over here. And this one's going to be 1.5 C, right, because it's going to come out 1 C relative to space-time, but he's moving this way. So, you know what I mean? It's going to be it's going to come out 1 C relative to space-time, but the black guy's moving the opposite direction in half a C. So it's going to be like 1.5 C, right? We said the blue man, right, he throws out a green light, right? It's going to, as he moves to the right, he's going to uncompress the waves, right, the photons, right? But the photons are going to come out at 1.5 C, right? I mean, relative to the men, right? And I was saying, when it bounces off of the black guy, right? Because this red guy, he can't see the photons hitting the guy. All he sees is the photons come back and hit him in the eyes. Then he can see, right? So when it comes back, if you're going constant velocity, everybody knows that Doppler effect cancels itself out. So this uncompressing will compress on the way back, you know what I mean? And it will compress in the same way so that he gets green light back, right? You know what I mean? It'll be the same, whatever. And the thing is, it's going 1.5 C this way, but this way it's going 1/2 C, right? So if you divide that by 2, because there's two ways, you know what I mean? It'd be 2C divided by 2. That means here we'll perceive the light went down here, came back, it's C, it's the same color, same energy, you know what I mean? Same way with the red guy. He'll send his off, right, at 1/2 C, right, relative to the men. But since he's moving into, every time he makes a photon, he's moving into it, making another photon. They're getting compressed, right? but when they bounce off of him and bounce back, they will decompress to the same exact whatever, right? So you get the same color. Then it's going half C this way, but it's going 1.5 C the other way. If you average that, it's going 1 C. So those two guys are perfect. The green guy is perfect. The only thing that's wrong is that black guy. He's going to see, if this is going 1/2 C, and this is going 1.5 C, well, what's his deal? You know what I mean? That ain't going to work out. Then I sat here for about 8 hours, and I thought about it, and I looked at this stinking picture for about 8-10 hours, right? Then it hit me, okay? This is what's going on, okay? This man right here, if both these men shoot out green light, you know what this guy will see? He'll see green light. You know why? It's so freaking obvious. A child could have figured this out. You know why he'll see green light? Look down here in the bottom here, right here. Look at here's a guy standing still. He shoots a photon gun. Green light comes out, hits him. It's 1 C. The guy says it's green. You know why he says it's green? There's no such thing as green color. Colors are a mathematical construct. They're imaginary. They don't, orange, blue, these things don't exist. They're just things, imaginary crap that our mind puts in our head when it corresponds to a specific energy, okay? I always say a wavelength, you know what I mean? It's not no, it's energy, okay? See, the brain doesn't know what colors are. It knows what energy is, okay? So I want you to think about this, right? E, look at those formulas down here, right? E equals HF. F is frequency. The more frequency you have, the more energy you have, okay? So you can see the red guy has no frequency. This has more frequency, then even more frequency. So you got, this has the least energy, right? This had more energy, then even more energy. But I want you to flip that over, right? Momentum, okay, energy is also, right, where's my finger? Energy is also momentum times C, okay, or P times velocity, big P times velocity, all right? Now, that means if your thing is going more than faster than C, see how it says PC? But that's when you're going C, right? So we're going faster than C, right? And what happens when you make it faster than C? You get more energy, right? Well, what happens when you have longer wavelengths, right? You have like this, right? Like redshifted, right? Over here you can see that momentum, right? Is Planck's constant over wavelength, right? So the bigger the wavelength gets, right, the weaker the momentum is, meaning the weaker the energy is, right? So basically this green light, it's still, on a still whatever, it's going at C, it has a certain amount of energy, right? Now look at this one with the red. He lost a certain amount of energy by moving away from the photons that he produces. He uncompresses it, right? It gets less energy, okay? But guess what? It's going at 1.5 C, right? This guy here, the photons going this way is going at 1.5 C. So you get more energy by going faster, but guess what? You get less energy by uncompressing your wave, right? Because you know what I mean? That energy that you gain and that energy that you lose are the same exact energy. Yeah. Guess what? This light right here that is all uncompressed, moving at 1.5 C, it has the same exact energy as this energy over here. Because the compression here, compared to here, made it have more energy, but it ain't going as fast. So it cancels out. It all evens out. Same way down here with the blue. The red guy shoots off its things. Since he's moving into each photon that he makes, he's compressing it, right? But and that makes it more powerful, right? More energy. But it's also only going 1/2 C that in that direction, right? Relative to the people moving. So the energy that it gained by compressing is the same exact amount of energy that it loses by going only 1/2 C. And the opposite happens over here. So what's my point? If these all have the same energy as green light going at steel, going at C relative to people standing still, right? That means, see, your brain doesn't interpret anything except energy, right? So if all of these are the same energy, right? The blue man hits them with photons, the red man hits them with photons. Even if the green man got hit by photons by another guy just standing next to him, all of them are going to perceive green light. Why? Because your brain gets a certain amount of energy, and then it corresponds that energy, amount to a color. And all three cases here, all these things, you have the same exact amount of energy, right? So when this blue man shoots out the green light, this black man sees green light because the energy gained and the energy lost are even. So it hits his photon collectors, his eyes, and then guess what? His eyes say, oh, this is green light. Oh, this is green light also. They're both green light. It doesn't. And then this is where the two-way communication comes in. The two-way communication is not to flip, so that, like I said, the blue man, he'd send out some green light and it would get decompressed, but on the way back, it would get compressed, you know what I mean? No. Your atoms and your synapses and all that crap doesn't have to do that because you're going to already perceive it as green light. You don't need it to come back and whatever. You're going to perceive it as green light because, like I said, you lose energy by decompressing, but you gain energy by speed. Over here, you lose energy by low speed and you gain energy by compression. They even out. You're going to get the same energy, so therefore your brain is going to interpret as having green light with the same energy. So we figured out how, because I couldn't think, well, how is this black guy going to think, that's how the energy gained is the energy lost by this extra speed or the lower speed. They all cancel each other out, so you got green light at the end. So he doesn't have to do some weird freaky thing in his brain to, interpret it in green light, you know what I mean? Math will do it, You'll have that energy of a green light. So let's use this. And the reason why you have the Planck length being the way I said it was, right, being a back and two-way communication, right, is basically not to flip over, flip this into what it, going this way, coming back, it's going to be flipped the opposite way. No, not to do that, because you already do that with your brain, right? Because you only interpret energy, not wavelengths and speed. The reason why you have to have two-way communication is because you have to know how long a second is, a Planck second. Okay, that's all it's about. We'll get into some examples first. Let's go into this right here. You can see on the bottom left, you see a hand here. That's like from a clock, right? And when that clock hand is made of a whole bunch of atoms. See how I got 4 atoms down here, or 5 atoms? Now when you need that, the motor wants that hand to go, move, rotate, because the next second or minute or hour is up, you know what I mean? This photon, in the hand, it's going to set, what I was saying before is that he throws a photon, right, or an information. Every time I say photon, I mean information carrier. He throws an information carrier to the next atom and moves, rotates, you know what I mean? Then the next atom throws a photon or an information carrier to the third atom, and he moves, and then third one, so on and so forth, until all of them have got the information and all of them have rotated, okay? But then if you move, right, now your hand is right here, the first atom throws a photon and moves, but if he throws another photon and the whole frame is moving, then this second atom, right, is going to be moved over here by the time he's not going to throw it up it's going to throw it at a diagonal thing.